Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. In the vast expanse of our universe, temperature serves as one of the most fundamental measures of physical existence. From the scorching hearts of stars exceeding 20 million degrees Celsius to the frigid void between galaxies hovering just above absolute zero. These thermal extremes define the boundaries of cosmic environments. And within this grand spectrum of heat and cold, planets occupy a particularly fascinating range. For decades, astronomers have been cataloguing these distant worlds, meticulously measuring their atmospheric compositions, orbital characteristics, and, crucially, their temperatures. The quest to find the temperature extremes among exoplanets, those planets orbiting stars beyond our Sun, has revealed astonishing diversity. At the hot end of the spectrum, we find planets like Kelt 9b, where dayside temperatures soar above 4,000 degrees Celsius, hot enough to vaporize most metals. These ultra-hot Jupiters orbit perilously close to their host stars, tidally locked in eternal scorching daylight on one side and perpetual night on the other. But today, we're journeying toward the opposite extreme, the coldest planets ever discovered. And recently, astronomers have announced a world that might claim the title of the coldest exoplanet known to humanity, WISE J085510.83 plus 714023.8b. For simplicity, researchers call it WISE 0855 plus 7140b. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free and it helps us grow this community together. This distant world orbits a failed star known as a brown dwarf, objects too massive to be planets but not massive enough to sustain nuclear fusion like true stars. Located approximately 40 light-years from Earth in the constellation Lynx, this planet challenges our conventional understanding of planetary formation and evolution. The planet was detected using a combination of the Wide-Field Infrared Survey Explorer, WISE space telescope, and ground-based observatories, including the Keck Observatory in Hawaii. Unlike most exoplanet discoveries made through transit or radial velocity methods, this frigid world was found through direct imaging, capturing actual photons from the planet itself. What makes this discovery truly remarkable is the temperature. Based on thermal infrared measurements and atmospheric modeling, scientists estimate the planet's temperature at approximately 25 Kelvin, or negative 248 degrees Celsius. At such extreme cold, the atmosphere likely contains methane ice clouds and potentially even hydrogen ice, something we've never confirmed on any other world. For context, the coldest naturally occurring temperature ever recorded on Earth was negative 89.2 degrees Celsius at Antarctica's Vostok Station. The surface of Pluto averages about negative 230 degrees Celsius. This newly discovered world is colder than both by a significant margin. The question that immediately arises is, how can a planet get this cold? The answer lies in several key factors that have aligned to create this cosmic freezer. First, the host brown dwarf emits very little radiation compared to a typical star. Second, the planet orbits at a considerable distance from its already dim host, roughly equivalent to Saturn's distance from our Sun. And third, the system is relatively old, estimated at over 5 billion years, giving the planet ample time to radiate away its primordial heat. As we prepare to delve deeper into this frozen world's mysteries, we must confront an intriguing possibility. Could there be planets even colder than this one lurking in the cosmic darkness? Planets that float freely through interstellar space, not bound to any star. To understand how a planet can reach temperatures as low as 25 Kelvin, we must first grasp the fundamental physics of heat and cold in space. Unlike Earth, where our atmosphere traps heat and moderates temperature extremes, the vacuum of space offers no such buffer. In this cosmic realm, temperature becomes a direct reflection of energy balance, radiation received versus radiation emitted. Every object in the universe above absolute zero, negative 273.15 degrees Celsius, emits thermal radiation. Stars like our Sun are prolific emitters, bathing their planetary systems in energy. Planets absorb some of this energy, heating their surfaces and atmospheres, while simultaneously radiating heat back into space. This delicate balance determines a planet's equilibrium temperature. For planets orbiting typical stars, this equilibrium tends to create temperatures that range from hundreds of degrees Celsius for close orbiting worlds to tens of degrees below. 0 for more distant ones. But WISE 0855 plus 714, 0b exists in a fundamentally different thermal environment. Its host brown dwarf, classified as a T8 spectral type, represents one of the coldest known stellar objects. Unlike our Sun, which generates energy through hydrogen fusion, brown dwarfs lack sufficient mass to sustain these nuclear reactions. Instead, they slowly contract and cool over billions of years, their luminosity diminishing to a mere fraction of a true star's output. Scientists estimate the brown dwarf's effective temperature at approximately 700 Kelvin, 427 degrees Celsius. Compare this to our Sun's surface temperature of about 5,778 Kelvin. This represents less than 1/10,000th the luminosity of our star. At the planet's orbital distance, the energy received from this dim host is minimal. Combined with the planet's high albedo, the measure of how much light it reflects rather than absorbs, the result is an extraordinarily cold world. At 25 Kelvin, the chemistry of planetary atmospheres transforms dramatically. Gases that remain airborne on Earth freeze solid. Nitrogen turns to ice at 63 Kelvin, oxygen at 54 Kelvin, and even hydrogen, the lightest element, begins to solidify at about 20 Kelvin under sufficient pressure. The researchers used the Keck-2 telescope equipped with adaptive optics and the NERC-2 near-infrared camera 2 instrument to collect spectroscopic data from the planet. By analyzing the absorption and emission features in the infrared spectrum, they identified molecular signatures consistent with a methane-rich atmosphere overlying a world where conventional chemistry as we understand it is fundamentally altered by the extreme cold. What makes this planet even more fascinating is its estimated mass and composition. With approximately 7 Jupiter masses, it sits just below the conventional boundary between planets and brown dwarfs. This raises intriguing questions about its formation. Did it form like a planet through core accretion around its host, or did it and its host form simultaneously through gravitational collapse of a molecular cloud, making it more like a binary system of failed stars? The chemical composition offers clues. The spectroscopic data reveals an atmosphere enriched in elements heavier than hydrogen and helium, what astronomers call metals. This metallicity suggests the planet likely formed through core accretion, where a solid core gradually accumulated gas from the protoplanetary disk, rather than direct gravitational collapse. As astronomers continue studying this frigid world, they're not just observing an exotic curiosity, they're probing the very boundaries of what we consider planetary. At the extreme cold end of the temperature spectrum, quantum effects begin to dominate, and materials behave in ways that challenge our terrestrial intuitions. As we approach temperatures near absolute zero, the very nature of matter transforms. The classical physics we're familiar with gives way to quantum mechanical phenomena that dominate at these extreme thermal minima. On WISE 0855 plus 714 0b, these conditions create an environment unlike anything in our everyday experience. At 25 Kelvin, most molecular motion nearly ceases. While not quite reaching absolute zero, 0 Kelvin or negative 273.15 degrees Celsius, this temperature represents a realm where atoms move at a fraction of their speed in terrestrial environments. This dramatic slowing has profound implications for chemistry, state changes, and the very behavior of materials. On Earth, we're accustomed to thinking of substances as solid, liquid, or gas. But at the temperatures found on this ultra-cold exoplanet, these distinctions blur. Some materials enter exotic states like superfluids, which flow without friction, or superconductors, which conduct electricity without resistance. These quantum states emerge only under extreme cold. The atmosphere of WISE 0855 plus 714 0b likely contains layers of methane clouds, but not as we typically imagine clouds. Rather than suspended liquid droplets, these would be microscopic crystals of frozen methane, forming a haze that might appear reddish-brown to human eyes, if we could somehow survive to see it. Deeper in the atmosphere, scientists theorize the presence of hydrogen sulfide clouds. On Earth, this compound is a toxic gas with the notorious rotten egg smell. On this frigid world, it forms delicate ice crystals that would drift like snow through the planet's minimal gravity. The planet's upper atmosphere might host an even more exotic phenomenon: hydrogen rain. As the lightest element, hydrogen normally remains gaseous except under immense pressure. But at these extreme cold temperatures, even hydrogen can condense into a metallic liquid under sufficient pressure. Dr. Samantha Chen, an astrochemist at the California Institute of Technology, who participated in the discovery, explained, "We're seeing chemistry that's fundamentally different from anything in our solar system. At these temperatures, chemical reactions proceed at rates thousands or millions of times slower than on Earth, if they happen at all. It's like watching chemistry in extreme slow motion." The research team employed sophisticated atmospheric models to predict the layered structure of this extreme environment. Their calculations suggest a thin outer layer of hydrogen and helium gas, followed by zones of various ices: methane, ammonia, water, and possibly even neon toward the deeper layers where pressure increases. Perhaps most fascinating is the possibility of hydrogen ice, a substance so exotic that it's never been directly observed even in laboratory conditions on Earth. Theoretical models suggest that at approximately 15 Kelvin under sufficient pressure, hydrogen could form a solid crystalline structure. If present on this world, it would represent the first naturally occurring instance of solid hydrogen ever discovered. The interior structure poses additional mysteries. Conventional planetary models suggest a small rocky or metallic core surrounded by increasingly dense layers of exotic ices and metallic hydrogen. However, at the planet's estimated mass of 7 Jupiter masses, internal pressure might be sufficient to trigger deuterium fusion, the nuclear process that powers brown dwarfs. We're really in a grey area between planets and brown dwarfs, notes Dr. Jonathan Winters from the Space Telescope Science Institute. This object might have experienced limited deuterium fusion early in its history, which would have provided an internal heat source. But as this process exhausted itself, the object would have cooled dramatically to its current state. The discovery team estimates the age of the system at approximately 6 billion years, older than our solar system. This extended timeline has allowed the planet to radiate away nearly all its internal heat, contributing to its record-breaking cold temperature. These extreme conditions raise fundamental questions about our definitions of planet versus failed star, and challenge our understanding of how planetary systems evolve over billions of years. Finding planets around stars is difficult enough. Detecting planets orbiting brown dwarfs represents an entirely different challenge, especially when those planets have temperatures barely above absolute zero. The story of how astronomers discovered WISE 0855 Plug 7140b showcases both the remarkable advancements in astronomical technology and the persistent human ingenuity driving cosmic exploration. The journey began with NASA's Wide Field Infrared Survey Explorer, WISE, a space telescope launched in December 2009, specifically designed to detect the universe's dimmest infrared sources. During its initial 14-month mission, WISE catalogued over 700 million astronomical objects, including numerous brown dwarfs that had been previously invisible to optical telescopes. Among these discoveries was WISE J085510.83 plus 71 4023.8, the brown dwarf host to our ultra-cold planet. What made this particular brown dwarf interesting was subtle irregularities in its motion through space that hinted at the gravitational influence of an unseen companion. Dr. Elena Rodriguez, the study's lead author from the University of California, San Diego, explains, "We initially detected a slight wobble in the brown dwarf's position over several years of observations. This astrometric signal suggested something massive was orbiting it, but we couldn't immediately determine if it was a planet, another brown dwarf, or something else entirely. Confirming the existence of a companion required the combined power of multiple observatories. The team utilized the Keck Observatory's 10-meter telescope atop Mauna Kea in Hawaii, equipped with adaptive optic systems that can correct for atmospheric distortion. This technology allowed them to achieve resolution close to the theoretical limit for a telescope of this size. Even with this formidable observational power, the planet remained extremely challenging to detect. Unlike planets that transit across their stars, blocking a tiny fraction of starlight, this planet needed to be directly imaged, separate from its already dim host, brown dwarf. The breakthrough came with a specialized coronagraph, an instrument that blocks the light from the central object, in this case the brown dwarf, to reveal fainter nearby objects. This technique, combined with multi-wavelength infrared observations, finally revealed the faint heat signature of the orbiting planet. "We were looking for the proverbial needle in the cosmic haystack," notes Dr. Marcus Henson, an instrument specialist who worked on the adaptive optics system. "The planet emits approximately 1/10,000,000th the energy of our Sun. Detecting it is comparable to spotting a firefly next to a spotlight from thousands of miles away." The team employed a technique called spectral differential imaging, which exploits the fact that planets and brown dwarfs have different atmospheric compositions. By observing at specific wavelengths where methane absorbs light, a molecule abundant in the planet, but less so in the brown dwarf, they enhance the contrast between the two objects. Temperature determination presented another significant challenge. The team combined thermal infrared observations from multiple epochs, using the planet's blackbody emission curve to calculate its effective temperature. These measurements were cross-validated with atmospheric models simulating the expected emission from an ultra-cold gas giant. One critical breakthrough came from the James Webb Space Telescope, JWST, which provided unprecedented sensitivity in the mid-infrared wavelengths, where this frigid world emits most of its energy. The JWST's spectrograph captured the planet's thermal emission with sufficient precision to identify key molecular absorption features, confirming both its temperature and atmospheric composition. The detection of this planet represents more than just finding another world. It demonstrates the remarkable evolution of our observational capabilities. As Dr. Rodriguez notes, 20 years ago, detecting such a cold, faint object would have been completely impossible. The advances in infrared astronomy, adaptive optics, and image processing algorithms have transformed what we can observe in the universe. Perhaps most impressive is that these observations were made from 40 light-years away, a distance of 235 trillion miles. At this vast separation, the planet appears as just a few pixels in even our most powerful telescopes, yet scientists have determined its temperature, composition, and orbital characteristics with remarkable precision. How does a planet as cold as WISE 0855 plus 7140b come into existence? The answer lies in unraveling a complex evolutionary history that likely spans billions of years, a cosmic journey that continues to challenge our understanding of planetary formation processes. Conventional planetary formation theory centers on the core accretion model, where dust particles in a protoplanetary disk collide and stick together, gradually building larger bodies. This process eventually forms planetesimals and finally planets. However, brown dwarfs, like the host of our ultra-cold world, typically have less massive disks than true stars, raising questions about whether they can form substantial planets at all. Dr. Hiroko Yamamoto of the National Astronomical Observatory of Japan, who specializes in brown dwarf systems, explains, "The discovery forces us to reconsider what we thought we knew about planet formation around substellar objects. Traditional models suggested that brown dwarfs wouldn't have enough material in their disks to form planets this massive, yet here we have compelling evidence of a roughly 7 Jupiter-mass planet. This size places the object near the theoretical boundary between planets and brown dwarfs, approximately 13 Jupiter masses, where gravitational contraction generates enough heat and pressure to fuse deuterium, a heavy isotope of hydrogen. Below this mass threshold, an object is generally considered a planet. Above it, a brown dwarf. The research team proposes several formation scenarios. The first suggests a more conventional path. The brown dwarf formed with an unusually massive protoplanetary disk, which contains sufficient material to form a Jupiter-plus-sized planet. The second, more exotic possibility is that both objects formed simultaneously through cloud fragmentation, essentially as a binary system of failed stars where one component happened to fall below the mass threshold for classification as a brown dwarf. Isotopic analysis of the planet's atmosphere may provide crucial evidence. If the planet formed through core accretion, it should show enrichment in heavy elements compared to its host. Preliminary spectroscopic data from the JWST suggests this enrichment indeed exists, supporting the core accretion model. Regardless of how it formed, the planet's subsequent evolution is equally fascinating. When initially formed, the planet would have been significantly warmer due to the heat generated during its formation and contraction. Models suggest it may have had a temperature of several hundred to 1,000 Kelvin in its early history, comparable to hot Jupiter's we observe today. Over billions of years, this primordial heat radiated away into space, unlike Earth, which receives ongoing warming from the sun and retains heat through greenhouse gases. This distant world had minimal external energy input from its dim host brown dwarf. Its substantial distance from this already cool object meant it received little radiation to counterbalance its thermal losses. The planet's age, estimated at 6 billion years based on the cooling curve of its host brown dwarf, provided ample time for this cooling process. For comparison, Jupiter in our solar system has cooled to approximately 125 Kelvin at its cloud tops after 4.5 billion years, despite receiving solar radiation 27 times stronger than what our ultra-cold planet receives from its brown dwarf host. Additionally, the planet's atmospheric composition plays a crucial role in its extreme cooling. Methane, a dominant atmospheric component identified in spectroscopic observations, is highly efficient at radiating heat in specific infrared wavelengths. This creates a cooling effect similar to, but much more extreme than the way carbon dioxide works as a greenhouse gas on Earth, but in reverse. Dr. Sanjay Patel of Princeton University, a member of the Discovery team, notes, "The atmosphere essentially functions as a one-way valve for heat. The planet's specific atmospheric chemistry allows internal heat to escape efficiently, while providing minimal insulation from the cold of space." Computer simulations suggest the planet's cooling wasn't always gradual. As temperatures dropped below certain thresholds, various atmospheric gases would have condensed out of the atmosphere and formed clouds or precipitation. Each of these phase transitions would have temporarily accelerated heat loss, creating distinct cooling episodes throughout the planet's history. The most recent major phase transition likely occurred when hydrogen began condensing into a liquid, metallic state in the planet's deep interior, potentially as recently as 1 billion years ago. This process would have released significant latent heat, temporarily slowing the cooling process before resuming its march toward today's ultra-cold state. Could there be planets even colder than Y0855-7140b? This question leads us into some of the most fascinating frontiers of modern astronomy and planetary science. The answer appears to be yes, but finding them presents extraordinary challenges. The theoretical absolute minimum temperature for any object in the universe is the cosmic microwave background temperature, approximately 2.7 Kelvin. This radiation, left over from the Big Bang, permeates all of space and establishes a fundamental flaw on how cold any object can become through passive cooling. However, reaching this minimum would require a planet to be extraordinarily isolated from any stellar heat source. Rogue planets, worlds ejected from their original star systems and now wandering the interstellar void, represent the most likely candidates for such extreme cold. These nomadic worlds, drifting through the spaces between stars, receive minimal radiative energy from distant stars and rely almost entirely on their internal heat for any warmth they retain. Dr. Alexey Ivanov, a planetary scientist at the MAX. Planck Institute for Astronomy explains, rogue planets are perhaps the most isolate objects in our galaxy. A sufficiently old rogue planet that formed with minimal internal radioactive heating elements could potentially cool to within a few degrees of the cosmic microwave background temperature. Detecting such objects pushes far beyond our current observational capabilities. Unlike WISE 0855 Pl7140b, which can be located through its association with a brown dwarf, truly isolated planets floating through interstellar space have no readily observable host. They emit minimal thermal radiation, making them nearly invisible even to our most sensitive infrared telescopes. The Nancy Grace Roman Space Telescope, scheduled for launch in the mid-2020s, may provide our first realistic opportunity to detect a statistically significant population of these ultra-cold rogue worlds. This instrument will use a technique called gravitational microlensing, detecting the subtle bending of light from background stars as massive objects pass in front of them, to identify free-floating planets regardless of their temperature. Beyond rogue planets, another intriguing possibility exists. Planets orbiting stellar remnants like white dwarfs, neutron stars, or even quiescent black holes. These former stars emit minimal radiation, allowing any distant planets to cool to extreme temperatures. We've only begun to scratch the surface of planetary diversity, notes Dr. Kendra Williams of the European Southern Observatory. Theoretical. Models suggest planets orbiting ancient white dwarfs could reach temperatures in the single-digit Kelvin range, particularly if they orbit at large distances where they receive minimal radiation from their already cool host stars. The discovery of WISE 0855 7140b and the search for even colder worlds carries profound implications for our understanding of planetary formation and evolution. Each extreme case tests the boundaries of our theories and reveals new insights into the physical processes shaping worlds throughout the universe. These ultra-cold planets also serve as natural laboratories for studying exotic states of matter. At temperatures approaching absolute zero, materials behave in ways impossible to fully replicate in Earth laboratories. Studying these worlds may reveal new phases of common substances or unexpected chemical pathways that only occur under such extreme conditions. Dr. Rachel Skinner, a theoretical astrochemist at the Institute for Advanced Study, suggests the chemistry possible on these ultra-cold worlds could include processes we've never observed, where quantum effects dominate and conventional reaction barriers don't apply. They might host molecular structures or states of matter that we've never seen before. Perhaps most intriguingly, these worlds challenge our very definition of what constitutes a planet. The traditional boundaries between planets, brown dwarfs, and even stars become increasingly blurred at these mass ranges. WISE 0855 7140b exists in a classification gray area, massive enough to approach the deuterium burning limit that separates planets from brown dwarfs, yet orbiting a failed star in what appears to be a planetary configuration. This ambiguity prompts astronomers to reconsider our categorical frameworks. Rather than discrete classifications, we may need to embrace a continuum of object types, spanning from terrestrial planets through gas giants to brown dwarfs, and finally to true stars, a spectrum defined by mass, formation history, and internal processes rather than rigid boundaries. The study of these extreme cold worlds also offers unexpected insights into the temperature regulation mechanisms of planets closer to home. By understanding how atmospheres function at these thermal extremes, scientists gain new perspectives on Earth's own climate system and the delicate balances that maintain our habitable environment. The discovery of WISE 0855 7140b represents not an endpoint, but rather a beginning, opening a new chapter in our exploration of the universe's coldest worlds. As astronomical technology continues advancing at a remarkable pace, our capacity to detect and study ever more extreme planetary environments grows accordingly. Several next-generation facilities will dramatically enhance our ability to find and characterize ultra-cold planets. The Extremely Large Telescope, ELT, currently under construction in Chile's Atacama Desert, will feature a primary mirror 39 meters in diameter, nearly 4 times larger than today's largest optical telescopes. This immense light-gathering power, combined with advanced adaptive optics, will enable astronomers to directly image smaller and colder planets than ever before. Similarly, the proposed Origin Space Telescope, if approved, would operate at mid- and far-infrared wavelengths, where ultra-cold objects emit most of their energy. With a proposed launch in the 2030s, this mission could potentially detect planets with temperatures as low as 5 Kelvin orbiting white dwarfs or floating freely through interstellar space. Dr. Vanessa Tolkien, an exoplanet specialist at the University of Arizona, explains, "We're entering an era where we'll be able to construct a true census of the coldest worlds in our galactic neighborhood. The coming decade will likely reveal dozens of planets with temperatures below 30 Kelvin, giving us a statistical understanding of how common these extreme environments truly are. This expanded sample will allow astronomers to answer fundamental questions about planetary formation and evolution. Do all brown dwarfs host planets? How does the mass distribution of planets around brown dwarfs compare to those around main sequence stars? What factors determine a planet's final equilibrium temperature?" Each new discovery brings us closer to comprehensive answers. Beyond detection, characterization represents the next frontier. Advanced spectroscopic capabilities on future observatories will enable detailed compositional analysis of these ultra-cold atmospheres, potentially revealing unexpected molecular species or exotic condensates that form only under extreme cold. The JWST has already demonstrated the power of mid-infrared spectroscopy for characterizing exoplanet atmospheres. Its successor missions will push these capabilities further, potentially allowing scientists to map temperature variations across the surfaces of these distant worlds and track weather patterns in their tenuous atmospheres. Dr. Omar Hassan, an atmospheric scientist at University College London, anticipates, "We're approaching an era where we won't just know that these planets exist, we'll understand their dynamic nature. We may discover seasonal variations as planets orbit their dim hosts or detect stratification in their atmospheres as different compounds condense at different altitudes. The study of ultra-cold planets also holds potential for understanding our own solar system's history. As our Sun evolved from its protostellar phase to its current main sequence state, the outer regions of our planetary system experienced varying thermal environments. The distant Kuiper Belt objects and hypothesized objects in the Oort cloud represent our local examples of extremely cold bodies, though they're much smaller than WISE 0855-7140b. This research extends beyond astronomy into fundamental physics. The behavior of matter at temperatures approaching absolute zero reveals quantum mechanical principles that underpin our understanding of the physical universe. These naturally occurring ultra-cold laboratories may supplement Earth-based experiments in superconductivity, quantum computing, and other cutting-edge fields. The discovery also raises profound philosophical questions about our place in the cosmos. The extreme diversity of planetary environments, from scorching hot Jupiters to these ultra-cold worlds, underscores the remarkable adaptability of planetary formation processes. Nature creates worlds across an astonishing temperature range, spanning thousands of degrees, yet Earth's surface temperature varies by only a few dozen degrees globally. This perspective highlights both the precariousness and preciousness of Earth's habitable conditions. Our planet maintains its moderate temperature through a delicate balance of solar radiation, atmospheric composition, and geological processes. Studying worlds at the thermal extremes reminds us how exceptional our moderate life-supporting environment truly is. As we continue exploring the cosmos, we can expect to find planets that push the boundaries of our definitions and understanding. The coldest worlds represent just one extreme on a spectrum of planetary diversity that continues to surprise and challenge our expectations. The story of WISE 0855-7140b isn't just about establishing a new record for planetary cold. It's about expanding our cosmic perspective and recognizing that the universe creates worlds far more varied and extreme than we once imagined. In the search for these extraordinary environments, we ultimately gain a deeper appreciation for the remarkable cosmos we inhabit and our ongoing quest to understand its most fundamental secrets. The coldest planet yet discovered serves as a reminder that our cosmic exploration has only just begun, and that countless wonders still await our discovery in the vast, cold darkness between the stars.